All right, chemists, we're going to start this lesson off by looking at trends that relate to what makes certain acids stronger than others. At the beginning, we have those three halogen acids we saw in our previous lesson, HCl, HBr, and HI. Notice HF is not considered a strong acid. It has a much smaller Ka value. And even though all three of these are strong, they don't all have the same strength. Their Ka values actually have different magnitudes. It's worth pointing out why. First, let's just write down the truth that it is stronger in this direction. And the reason for that has to do with how easy it is for each of these things to lose the H+. Remember, a strong acid is one that readily gives up its H+ ion. And the easier it is to do that, the stronger the acid. Well, in this case, what you have are longer bonds between the halogen and the hydrogen. So these are not currently drawn to scale, but what if I had to? I could have a little H attached to an iodide versus a little H attached to a bromine, a little H in a chlorine, and a little H in a fluorine, not perfectly to scale. But that gives you a sense of the fact that as you go down, the atomic radius gets larger and larger and larger, and then therefore the bond length is longer and easier to break. So a longer bond is easier to break. And that goes with a stronger acid. Now, there's another trend worth mentioning, and it's seen in both of these two columns of acids. Here we have oxyacids. All of these are oxygen-containing acids, and specifically have an H that gets lost, which is attached to an oxygen in every single case. Even though you can't tell in those chloroacids, that's still true. So in this case, we actually have a strength increase as you go from what's on the bottom to the top. And the reason is different. It doesn't have to do with bond length this time, because these are all OH bonds. We're breaking the same bond every time. So the reason for this is what else is attached farther out in the acid. And the trend is explained by the fact that you have more and more electronegative atoms that are attached to the bond that's being broken. So more electronegative atoms attached to the OH makes a stronger acid. And that's true if it's a different element, such as chlorine being more electronegative than bromine, in turn more electronegative than iodine, or just more of the same electronegative atoms. So perchloric acid is stronger than chloric, which is stronger than chlorous, which is stronger than hypochlorous, because you have more and more oxygen atoms attached. In fact, that's why those top two are strong acids. The others are relatively weak. So those are just some trends in acid strength that we're going to see further on, and they'll explain lots of things that we see about how these things react. The rest of today's lesson has to do with acids that can lose multiple hydrogens. These are called polyprotic acids. What do we do when you have something that's acidic and it can lose more than one H? Here's a structure of carbonic acid, for example, and both H's are acidic. Well, we treat them independently and they successively get lost one at a time. So carbonic acid can lose an H+, and the conjugate base is hydrogen carbonate, HCO3-. And that has some Ka value. We're going to call it Ka1, meaning the first acid dissociation. Happens to be 4.3 times 10 to the negative 7. But then the conjugate base that we just made also is acidic. It can lose an H. So we can write an equilibrium for this, losing an H+, and then the carbonate ion. And that has a Ka value as well. We call it Ka2, meaning how likely it is to lose the second acid. And you might guess, compared to the magnitude of the first Ka value, the second Ka value is even smaller. It's that much more difficult to remove an H from something that's already lost an H plus and is now negatively charged. So it's more difficult to lose successive H's. More difficult to lose successive H's. And this is how we treat any polyprotic acid. Another common one is phosphoric acid. That's a triprotic acid. So I'd like you to practice, hit pause, and see if you can just write the 3 equilibria that we would expect for phosphoric acid and the 2 conjugates that get made. Okay, let's see how you did. So H3PO4 loses an H plus, and then we have H2PO4 negative. H2PO4 negative loses an H plus, and you have HPO4 2 negative. Notice it's getting one more negative, one less positive each time. And lastly, hydrogen phosphate will lose an H plus and become phosphate, PO4 3 minus. And just for reference, let's look at the Ka values that go with each of those dissociations, Ka1, Ka2, and Ka3. These are tabulated and they only change with temperature. The first dissociation constant is 7.5 times 10 to the negative 3. The second one is 6.2 times 10 to the negative 8, much smaller. And the third one is even more orders of magnitude smaller, 4.8 times 10 to the negative 13. So as we saw with the case with carbonic acid, it's even more difficult to lose successive H's from phosphoric as you continue to lose them. Now let's see if we can use that information and go back to what we did in the previous lesson. How do we figure out the concentration of hydrogen ions in some solution of one of these polyprotics? Let's look at phosphoric first off. So we know that they lose their H's successively. So if I have a phosphoric acid solution, H3PO4, I'll start by just writing the dissociation into an H plus and an H2PO4 minus. And let's set up an abbreviated Rice chart. We have 5 molar of phosphoric acid. So I'm going to have 5 minus X of phosphoric acid. You'll create X hydrogen ions and X dihydrogen phosphate ions. But we're not done. We have 2 more successions after this. So then H2PO4 negative will dissociate and lose an H plus and become an HPO4 2 negative anion. And then how much of this do we have? We have X of the dihydrogen phosphate, and it's going to dissociate some small amount. So it will lose some of that X. Let's pick a new variable. How about Y? So now I have X minus Y of the dihydrogen phosphate. How much H plus do we have at this point? Well, we actually have X from the first dissociation. So now we have X plus however much Y we lose from the dihydrogen phosphate, because it's 1 to 1. And then how much hydrogen phosphate do we have? Just Y. But we're not done. There's actually one more dissociation to look at. So now hydrogen phosphate can lose an H plus and become phosphate. And here we have how much hydrogen phosphate do we have? We have Y. It's going to dissociate a very small amount. It will lose, let's say, Z. How much hydrogen ion do we have? Well, we have X plus Y from before, and then some new stuff, so we have actually the sum. X plus Y plus Z. And then how much phosphate do we have? Just Z. So we have 3 variables, and we have 3 equilibrium constants. Let's go back and use those and see if we can come up with an expression that would eventually get us how much H plus we have in this 5 molar solution. So Ka1, which is from up above, we have 7.5, 10 to the negative 3. I'm going to write that as a decimal. 0.0075 is equal to x squared divided by 5 minus x. And if we simplify this, we can assume that the x is negligible compared to 5. So this becomes x squared over 5. And we can solve for x, and we get 0.19. But I need to figure out what y and z are as well. So let's look at those Ka values. Ka2, which is 6.2 times 10 to the negative 8, is equal to the hydrogen concentration times the hydrogen phosphate concentration divided by the dihydrogen phosphate concentration. So that's x plus y times y all over x minus y. Now, know how we use these simplifications of thinking about differences from the dissociation being so small. We said that this x is negligible compared to 5 because this k is small. Well, Ka2 is even smaller, a lot smaller. So I don't know how much y we're going to lose from x, but it's probably going to be negligible compared to x. So that means this negative y is insignificant compared to x. Well, if x minus y is just x, that means x plus y is also just x. So we can actually neglect this plus y in the numerator and this negative y in the denominator, and you just get y. So without any math at all, we actually know that y is equal to the Ka2 value using that assumption. And that Ka2 is very small, so that's a good assumption. What I'd like you to do now is see if you can use the value for Ka3, write out the expression for Ka3 in terms of x and y and z, and come up with what z is equal to in terms of Ka3 and anything else. Okay, so Ka3 is 4.8 10 to the negative 13. And that's going to be equal to H plus times phosphate divided by hydrogen phosphate. So that's going to be equal to x plus y plus z times z all over y minus z. Now before we do math, let's think. We already said that x plus y simplifies to just x, so that plus y has to be insignificant. Well, if the y is insignificant compared to x, how is z going to compare to x? This z is from the dissociation of the third equilibrium constant, so it's really small. So I don't know how small this z is, but it's got to be negligible compared to y, which means it's also negligible compared to x. So we can actually get rid of the plus z and the plus y in the numerator. That means we can also get rid of the minus z in the denominator. So this simplifies to just x times z over y. We get a linear equation. Now we have a way of solving for all three of our variables, x and y and z. We already got x. I'll put a box around it. We actually already got y as well. Y is equal to Ka2, 6.2 times 10 to the negative 8. And then we can get z because we know that Ka3 we just determined is equal to x times z times y. So if we take the Ka3 value, 4.8, 10 to the negative 13, times the value we just used for y, which is Ka2, 6.2, 10 to the negative 8, and divide by x, 0.19, we get indeed a very small number, 1.6 times 10 to the negative 19. So what's our H plus concentration? Because we want a pH. So all of this we have to put together. Well, H plus is actually equal to the sum of x plus y plus z. Wait a minute. We just said that x plus y plus z just simplifies to x. So even though we calculated those other variables, all we really needed for this example was the first dissociation. We should really go back and check and make sure the 5% rule holds for those other simplifications, and indeed you'll find it does if you go back and do that. But that means at the end of the day, your H plus concentration is just equal to X, so your pH is the negative log of 0.19, and when you do that, you get 0.72. Now, it wasn't a waste to do all that extra work, because maybe we actually want to know what the phosphate concentration is, and that's equal to the variable Z. Or maybe we want to know what the hydrogen phosphate concentration is. That's equal to the variable Y. So this setup is still useful for polyprotic systems if you want to know the concentrations of other ions. We just happened to only need the first one in this example. And sometimes these won't be insignificant, and then you actually have to solve quadratics, but that'll never be the case on the AP exam as far as we've seen all the times they've asked. Okay, let's do 2 more examples, also with polyprotics, but this time we're going to take a look at when these simplifications do and sometimes don't always follow suit. And a good one to look at is sulfuric acid. Sulfuric acid is a polyprotic, but the first dissociation is strong. We said sulfuric acid is a strong acid, and it is, but really only the first dissociation is considered to be strong. The second one is often drawn as an equilibrium because it's not nearly as easy to lose. It's still pretty strong. Hydrogen sulfate is still pretty acidic, but nowhere near as acidic as sulfuric acid. So how do I factor both of these dissociations in when I want the pH of a 1 molar solution? Well, let's write out the dissociations that we have. Even though they're right there, I think it helps to just write them again. Sulfuric acid irreversibly becomes hydrogen sulfate and a hydrogen ion. Now, if we have 1 molar sulfuric acid, that first dissociation goes to completion. So we actually have 1 molar of the hydrogen sulfate and the hydrogen ion. This is such a big K value, it goes to completion. That means all I really have to look at is the second one. Hydrogen sulfate dissociates into an H plus and a sulfate ion. And now I have 1.0 minus X of the hydrogen sulfate. I actually have 1.0 plus X for the hydrogen ion and X for the sulfate ion. How did I get this 1 plus X over here? Well, we had 1 from the first association. X is now how much more I'm getting from the second association. In fact, you know what? Let's be consistent and let's call it Y, because I was using Y for the second association each time. Now I can use Ka2. Ka2 is 0.012, and that's equal to the products over the reactants. So that's going to be 1 plus Y times Y all over 1 minus Y. Now I'm going to take an assumption that this Y is insignificant compared to 1, which means both the 1 plus Y and the 1 minus Y just become 1, which means that Ka2 is equal to Y. Now my H plus concentration we defined earlier as 1.0 plus Y, which if you follow sig fig rules, notice what happens here. I have something precise to the tenths place, and I'm adding something to the thousandths. Even though at first you would write 1.012, with sig figs, those last 2 digits are insignificant. So 1 plus 0.012 is just 1.0 molar. And then your pH is the negative log of 1, which is exactly 0. So a 1 molar solution of sulfuric acid should be exactly 0 with that level of precision. Now, one more challenge problem for you to try after hitting pause, which is what happens when we do 2 things differently. We're making the solution more dilute. We're actually going to increase the percent ionization. And we have a more precise concentration. We have a 3 sig fig concentration as opposed to just a 2 sig fig concentration. How does that change the outcome of this? Still sulfuric acid, so same setup as above, but the numbers are different. Hit pause and see if you can go through this exercise and then come back and see how you did. Okay, so the first association goes to completion. So we have 0.01 molar from the first association of each of those ions. And I'm going to rewrite that, but I'm going to write it below the second association since it's already there. So I have 0.0100 minus X of the hydrogen sulfate. The sulfate concentration is just X. Actually, let's use Y, because that's what we've been using for the second dissociation, which this is. And then how much do I have of the H plus? We have 0.0100 plus Y, which means my Ka2, which is still 0.012, is equal to Y times 0.0100 plus Y all over 0.0100 minus Y. And if we take an assumption and say that those Y's are insignificant, I actually get that this is just Y. But then look what happens if you stop there and use that. If you plug that back in to this value, you'll get a negative number. And that does not make any sense. So clearly this doesn't work. Now that we have a greater percent ionization, a greater dissociation, we're not within the 5% rule. We're actually greater than 100%. So percent dissociation is not less than 5%, which means we can't simplify. And sadly, or perhaps delightfully, what that means is we have to solve a quadratic. And I'm not going to write out the quadratic, but if you expand this expression, just distribute everything and combine like terms, you get an expression that's y squared plus 0.022y minus 0.00012, and that's equal to 0. And if you solve that quadratic, you get a root that makes sense. It's 0.0045, which means our H plus concentration, which is 0.0100 plus 0.0045. Aha, we're doing addition. 4 sig figs, I get an answer to decimal places. 4 decimal places to 4 decimal places, I get 0.0145 molar H plus. And we can turn that into a pH. The pH, I'm not even going to write it, you just take the negative log of that, you get 1.839. Remember your rules for sig figs with pH. The number of significant figures in molarity is how many decimal places are in the pH. So 3 sig figs in the molarity become 3 decimal places in the pH. Okay, so much more involved mathematical thinking to do with polyprotic acids, but the key is that the dissociations happen one after the other. They all have their respective Ka values, and we can use those to solve for how acidic a solution of a polyprotic acid is.